Welcome to a short how-to video for heating things up. In this lab we were heating things up, specifically a house. So like in all introductions, we don't want to forget what parts to include. We want to include the question that we rewrite in our own words, our hypothesis, why we believe it, and the critical concept. So let's take a look at this lab's initial question. And heating things up had to do, as I said before, with heating a house in the winter isn't as always as easy as turning up the heat. So the question was, what variables affect the rate and amount of temperature rise in a solar house? So what kinds of things might we vary or change that would affect the rate that the temperature changes or doesn't change in a solar house using only the sun? I give you a variety of materials from aluminum, styrofoam, cups, caps, connectors, water thermometers, anything you really wanted to bring in, and of course always being safe around these kinds of things. And then your guess was as good as mine. I did want you, of course, to think about the latitude that you were building the house, because depending on how far north or south or perhaps at the equator it was, they're going to receive different amounts of energy, which is going to mean that you're going to have to design your house differently. And then design it differently so that the energy of convection, conduction, and radiation are you either able to move into or out of the house to keep it warm or cold, depending on where you're at. And we'll look more at that in just a few minutes. So the first thing that you'd want to do is take these materials, the light, the cups, the thermometers and things, and that would be the materials in action. A simple drawing of how you might use these different materials, and then go through the procedures that you used. I'll use a very simple example. Some of you came up with much more complex ones. So here's my example. Sorry for the audio problems. Things up lab. In this lab, what we're looking at is what are the different variables that might affect the way the temperature of a house rises or maybe doesn't rise. And so what we're trying to do here is find out the effect of radiant energy on different houses around the world. So if you happen to live in a place where it's very hot during the summer, then you're going to want to keep your house cool, and if it's very cold during the winter, then you're going to want to warm your house up. So using basic types of materials, what things could we vary to change the temperature inside the house? Well, we always want to have three, maybe four or five, or whatever number of variables that we shall choose, but we do want to keep one thing in control, and that would be, in this case, just the temperature of the sun if we didn't do anything to it. And then we're going to vary something. So let's just vary and see how the temperature gets affected by having a house made out of material that's completely black, and at the same time a house that's made out of something that's white. We'll do other things, other materials. We've got any type of reflector or conductor that we want to use. And so we start our timer here, and we keep track of how the temperature changes, both in our control and our two variables, and then we can record that information as we go through time. And that is the materials and the setup for heating things up. So from there, our procedures are going to give us some data, and that's where we show our information in our visual section. So the data for this particular lab, and the one that I'm showing as an example, is a very simple one, and I didn't do this very completely because, as you notice, I didn't put my units on there. So as I always say, no naked numbers, and there they are. So in any case, let's just say that we timed for 5 minutes and we made a temperature reading every 30 seconds. So we have our three different temperature readings, one for the control, the thing that in the experiment that we leave unchanged and test our variables against. And then we had our two variables, the black house and the white house. So let's just say that the control under the temperature of the light with no changes went up 1 degree every 30 seconds, whereas the black house, starting at the same temperature, rose about 2 degrees every 30 seconds, and the White House only went up about 1 degree every minute. So we have a range of different temperatures from 20 to 30, 20 to 40, and 20 to 25. We then use a bar graph to plot those, time being on our x-axis and temperature change on our y, and as you can see they all started at the same, but depending on whether it was the control or the White House, which really didn't have as much change. Maybe it had something to do with the reflecting the radiant energy, and then the black house had the biggest temperature change. So you can very easily see the change in temperature through time. Don't forget you should have a title, your scale on x and y axis, your labels with the units. I didn't put that there, but you can review any of that. And so this is our visual, and what it shows us, depending on what our hypothesis was originally, was the dark house absorbs more energy and therefore would be better in a colder climate, whereas the White House reflects more of the radiant energy. And as I said, many people got much more complicated on how they built their houses and the results that they would get. So let's move on to the conclusion. And in a conclusion paragraph, we want to use our data to explain the results. So first of all, were we right or wrong? What was the right answer? Again, I can't really tell you in this whether you were right or wrong or what the right answer was, because you picked your house to be in a particular place and you designed your house in a way that I can't really tell you whether you were right or wrong. It depends on the data that you got. So unlike many of the labs in the past, you really do have to look at your data and decide how did you do. It's really a design and inquiry kind of thing. We'll look at the critical concepts of conduction, convection, and radiation, and how radiant energy is different, as well as any misconceptions or unexpected results. So first of all, let's just do a quick review of conduction, convection, and radiation. Convection is the flow of material, primarily through the difference in density. As it gets hotter, it rises. As it cools, it sinks back down. Radiant energy are those rays or waves that travel from, say, the sun or from a hot heater, and it goes very fast, and it goes in a straight line. And in the case of the sun, it travels 93 million miles in about 8 minutes and 16 seconds. And then conduction is the touching, the molecular movement as one molecule bumps and vibrates and heats up. It moves from an area where it's very hot, and it continues to add heat up through that. So what happens in a house? Well, the convection allows the roof area to warm up. So if anybody tried to look inside the house at the difference between the floor and the roof, you'd see that roofs and attics tend to be warmer, and floors and basements tend to be cooler. In conduction, it's really the conducting through the barriers of the house. In our case, you may have found that aluminum conducted the heat really well, but styrofoam didn't conduct, and that's because really aluminum is a metal that's quite densely packed together, whereas styrofoam is mostly air, and air doesn't really conduct heat well because there's not much to touch. And then of course radiant energy is primarily through the roof or upper part, although it could come in the windows, which I didn't see anybody using, but windows are a great way to allow solar radiant energy into your house. And if that energy can get in, it can't get back out because it turns to heat energy in your house. So that's how we really need to focus on what these different elements of energy movement are. That's critical concept number one. And then I found this very interesting way to show what we've got here is the Earth moving around, and you know that the Earth is at a tilt, and as it moves through the year, that tilt changes from either towards the sun if you're in the northern hemisphere, or away from the sun in the northern hemisphere. So if you look over here, as the year changes, let's just say that you were here at the equator. As you get to spring, summer, and then fall, look at that. The energy is coming directly overhead if you're living at the equator. And so all that energy is going to be accumulated right there. And you're going to have a lot of energy. Now that's fine if you're in the northern latitudes. If you're in the northern latitudes in the middle of summer, you're going to get quite a little bit of light. And matter of fact, it's going to stay light just about 24 hours a day. But as you notice, we're moving into fall and winter. Look at the angle that the light is striking the person who's living in this house. And through winter, as we're approaching winter over here, the angle gets steeper and steeper, and pretty soon there's hardly any of that radiant energy hitting the surface. Look at that. Matter of fact, at a certain point in the winter, all the way up at the Arctic Circle where this house happens to be, the sun doesn't even ever rise above the horizon. So this is a fun little website. I'll include it in this part. And we'll quick head back to heating things up. Just as a reminder, let's get those conclusions done. And that's a not so brief review of heating things up. Hope you learned something.